Okay everyone, welcome back to lesson 3. In this video we'll talk about what a geometric sequence is, how that may be different from the last couple. We've talked about an arithmetic sequence, talk about some of the pieces, how to build that formula, and what we can do with it. So take a look at those sequences that you see on there. Before we get going into this, just remember the links to these files and the completed solutions will be in the description box should you wish to follow along, or if you try them on your own, check how you're doing, that sort of thing. You'll find those links underneath this video. Okay, so take a look at those sequences. 3, 15, 75 is the first one. And if you try to add something like we talked about with an arithmetic sequence, we talked about a common difference, you can add 12 to 3 to get 15. But the issue is you need to add 60 to get 75 from 15. So the problem here is it's not arithmetic because that difference should be common. So since adding doesn't work, we could say that this is not arithmetic. So there must be some other way to deal with it, which is what we're going to get into here. The same thing underneath won't work. However, you could think about not adding, but dividing, or in other words, multiplying by a fraction. So if you think about 512 and 256, they are related because 512 is double what 256 is. So you could multiply this by 1/2. Same thing, 256 gets multiplied by 1/2, 128 multiplied by 1/2, and you get each successive term. Now, while it's not arithmetic, it is still a sequence that we can deal with. We just have to think about it a different way. And the name we give these types of sequences is geometric. And similarly to arithmetic, there is still something that's common between the terms. In this case, just not addition, rather multiplication. So that geometric sequence is a set of numbers formed by multiplying by a constant, and that constant is a common ratio. Now previously we talked about a common difference, and you could find it by taking a term and subtracting the previous one. Similarly here, we can calculate it by taking a term and dividing by the previous one. Actually turning it into a ratio is one of the things you can do to find it. Now let's go build that formula. Now if you think about this and those sequences, well, our first term is just going to be our first term. Now if this is a common ratio, in order to get the second term, we could take whatever t1 is and multiply it by our ratio. This is what we did in those two sequences that you just saw. Now this is for t3. Just remember, whatever term 2 is, in this case t1 times a ratio, well, in order to get the next one, well, let's just multiply by another ratio. And what you'll notice is that it's very similar to arithmetic in the sense that whatever you're multiplying your first term by, you'll do that one less times than the number of your term. So let me put that into other words. Term 3 is going to be made by multiplying by your common ratio twice, always one less than your term number. By the same logic, term number 4 is going to be t1 multiplied by your ratio, well, not 4 times, always one less, so 3 times. t5, no exception, ratio 4 times, which means any term, the general term here, if I don't know which one it is I'm looking for, you can find it by taking your first term, multiplying by your ratio, and minus 1 times, always one less. So there is the formula for your general term of this geometric sequence. Okay, this will work for any single one. Okay, which is nice because there's the formula for it. Now we can use it to do a couple things. So if you think about why that ratio has to be non-zero, the ratio has to be non-zero, or every term, so let me do a bullet here. The ratio is non-zero, or every term after t1 will be 0. Right? If you think about taking a number and multiplying it by your ratio of 0, it just zeroes out every other term, which isn't really interesting to think about. Now, in a sequence with that common ratio of r, if it's negative, how can you predict if a specific term will be negative or positive? Now, you got to think about exponents here, because that's what this is based off of. Now, it depends on the exponent. Oops. It depends on the exponent, which really means it depends on what n minus 1 is, or it depends on what that value is. So if your exponent is an even, you will end up with a positive, right? You'll have enough for things to cancel out. Your negatives will cancel, so think about doing negative 2 to the power of 2. You're going to end up with positive 4, right? The negatives will cancel. If you think about having an odd exponent, you're always going to have one more negative, so your sign is always going to end up being negative out of that. Okay, so you can predict it based on the exponent. So let's go do a couple things. We can find the general term and the 7th term of these sequences. So we'll do, yeah, we could do both here. That's all right. Okay, the general term is essentially us finding a formula that will work for this specific sequence. Now, this formula we came up with will work for any sequence, but I want to find a formula that will work for this one, right? That'll be the general term of this sequence. So I know that the first term happens to be 2. I can see it in there. The only other thing I need to do this is a ratio. Now, if you think about going from 2 to 6, you can multiply by 3, but remember that it's got to be a negative 3, because that's a negative 6. So here's my ratio. If you take negative 6, multiply by negative 3, you'll get positive 18. So it does work. Or you can take one term, divide the previous, you'll still find out your ratio is minus 3. So there it is, n minus 1. So this formula will work for this specific sequence and no other sequence, only this one. So let's go find the 7th term now, knowing that. So T7 is going to equal 2. There's my ratio minus 3 in the exponent 7 minus 1. So we can calculate out what that 7th term happens to be by doing 2 times negative 3 to the power of positive 6. So your 7th term is 1,459, I believe. Let's just check to make sure. I think I did this one earlier and it ended up being weird, so maybe I'm off by a number. Minus 3 power 6. Oh, 1458. See, I knew something was weird. Let's fix this. So 1458 is the value of that 7th term. There we go. We can do the same thing for the other one. Even with fractions, this is still true. So our general term, right, Tn equal to T1 Rn minus 1. That's our formula. If you put in what you know, right, I don't know Tn. I know the first term's 1 over 3. My ratio. Well, if I take negative 1 over 6 and divide it by 1 over 3, well, I'm still going to get a fraction. So you can even plug it in here and make sure, see what happens. So negative 1/6, divide it by the previous term of 1/3, and you've got negative 0.5. So your ratio, negative 1/2, and n minus 1, n minus 1. So there's my general term. There's my general term. Now we can go use it, find the 7th. So T7 equal to 1 over 3, negative 1/2 is the ratio, 7 minus 1. So T7 equal to 1 over 3, negative 1 over 2 to the power 6. And again, you can grab your calculator, do that, and you end up with your 7th term being 1 over 192. Right, there's your 7th term. So you can find a formula that will work for any term, use it for the term we need. And in this case, the 7th term. Okay, so that's all good. That's pretty straightforward. And we can do some other things as well. We can locate how many terms are even in a sequence. So if I'm given this sequence here, and now is where things change slightly, you're not going to be told if it's arithmetic or geometric. That's the first thing we need to work on and decide, now that we know both. So if you take a look at this, 4 to 20. If you try to add, you have to add 16. But 20 plus 16 is not 100. So right off the bat, I know it's not arithmetic. So let's think about multiplying instead. Right, 4 to 20, you can multiply by 5. 20 times 5 also gets you 100. So that looks good. There's a ratio, right? It's 5. T1 is equal to 4. There's your first term in that sequence. And I don't know what term number this last value is. What I do know is it is the last value. So I know that Tn, I can use 7,812,500 as the value I want to find out what its term number is. I know the value of that term, just not what term it actually is. So there's the information I know. So let's use our general term to find what we need. So if you fill in what you know, 7,812,500 is equal to, T1 is 4, ratio of 5, and minus 1. Okay, so here's what I know. So let's simplify some things a little bit. We can get rid of that coefficient 4, and you can divide a 4 on both sides. Right, so divide by 4, divide by 4. So 7,812,500 divided by 4, and we get this number. Hang on here, so 1,953,125 is equal to 5 to the power of n minus 1. Now here's where we got to do a little bit of guessing and checking. At this point in this course, we don't really talk about how to solve for something that's in an exponent. At this point, it really is a guess and check kind of situation. So think about having a base 5 and finding some exponent to get us this number. And if you think about it, well, 5 cubed isn't enough, right? That only gets me 125. 5 to the power of 10 happens to be way too big, right? So there's a range. So let's try 5 to the power 9. And there's the exact number that I need. So I know that 1,953,125 is equivalent to 5 to the power of 9. Those are equal. Now what I'm able to do is, well, take a look at those exponents. Right? The base is the same of 5. The result is the same thing. So it's the exponents that also have to be equal to each other. That's a natural consequence of this. So that means n minus 1 has to be equal to 9. So if I solve this little tiny equation now, I know that n is 10. Therefore, the sequence has 10 terms. Right? It's a little bit of guessing and checking, but the numbers usually aren't too large. Especially when you're working with powers that big, the value grows very, very quickly. So it is relatively easy to find it. Okay? If you look at example 2, in a finite geometric sequence, the first term is 5, the fifth term, 1,280. Determine the second term and the sixth term. The issue here, I don't know what the ratio happens to be, so I'm going to need to find that. So let's think about what our formula allows us to do here first. So Tn is T1 ratio n minus 1. A couple things I do know. I know the first term already. That's a good thing. So I know that the first term is 5. I know that T5 is also 1280. This could also be Tn if I made n equal to 5. So that's going to be really helpful for us in finding the ratio. So let's go find the ratio first. So we can translate some information here, where let's make Tn 1280 equal to the first term of 5, ratio unknown, n minus 1. Well, I used 1280 for Tn, which means that was T5, which means n is 5, which means this is 5 minus 1 as my power. If you simplify it a little bit, 1280 is equal to 5, r to the power of 4. I could divide both sides by 5 to cancel out that coefficient. So 1280 divided by 5. 256 is a number that I end up with. 256 is equal to r to the power 4. Now I've got to reverse engineer this exponent to solve for r. Essentially, this is like taking the fourth root, like you would take a square root for something else if it was a power 2, but this is a fourth root. So if you take the fourth root of 256, you will find out that 4 is your ratio. And you can try this by doing 4 to the power of 4, and you will see it's also 256. This calculator has a fourth root option in here as well, but you just have to tell your calculator what root or index you want to use. So I'm going to hit a 4 first, and then my math button, and then I can pick option number 5 here, which will tell my calculator, hey, do the fourth root of this radicand, 256. There's my 4. Okay, so there's my ratio. Now that I have it, it's very, very nice to find out what the second term is, because I already know the first term. So T2 is equal to T1 multiplied by the ratio. So T1 is 5, the ratio is 4, T2 is equal to 20. That's perfect. T6 is the other one I need, so I know T5. T6 is equal to T5 times the ratio again to get to the next term. So the fifth term is 1280. Multiply that by 20. Multiply by a ratio of 4. So the sixth term here is 5,120. Let me just double check. I feel like that's right, but I've been wrong in the past. There we go. Right, there's our sixth term. Okay, so it looks good. If I know what one term is and I know the ratio, I can build the next consecutive one. Okay, so let's look at this a little different. Let's look at part B. So the last term of the sequence is 20,480. Last term is 20,480. How many terms are there in this sequence? So these two are linked, so all of this information is still true. So I know the first term again is still 5. Right, so T1 is still 5. The term in question has a value of 20,480. Again, I don't know which term that is. All I know is this is the last one. So I'm looking for n here again to make sure that this 20,480 term is the last term in the sequence. We found the ratio together. It's 4. I have everything that I need to be able to do this. Right, here's my general term formula. T1r to the power n minus 1. Fill in what you know. So 20,480 is equal to, well, T1's 5, ratio 4, n is unknown. Again, this is another one of those cases where I'm looking for the variable that is in the power. So I'm going to have to do a little bit of guessing and checking. Let's make the number smaller here first. You can take your left side of the equation and divide by 5. Okay, that'll cancel out your 5's here. Don't multiply it into the set of brackets. 5 times this ratio is not 20 because that exponent is only being applied to the 4, not the 5. So if you put the 5 in the brackets, it then says the exponent's going to it as well. So just be careful how you deal with simplifying this. So it's helpful to get rid of it first. I find that to be one of the easier ways to do this. So divide by 5. So 4096. Let's get our purple color back. 4096 should be equal to 4 to the power of n minus 1. A little bit of a guess and check here. So let's do 4 to the power of 6. Perfect. So 4 to the power of 6 is the same thing. Once you figure that out, make your exponents equal to each other, and then you can find out the value of n. So n minus 1 should be 6. That means n is 7, which then tells you that there are 7 terms in this sequence. Okay, there's 7 terms in the sequence. N is 7, which really means that T7 is equal to 20,480. Right, that's the 7th term. Okay, so all looks good. I can still do a lot of the same things that we did in arithmetic sequences with geometric as well. This is where we start to talk about some of the applications. So geometric series and sequences are where more of the applications start to happen. So this one says a ball is dropped off the roof of the school, Lillian Osborne, which has a height of 4 meters. After each bounce, the ball rises to 60% of its previous height. Determine the height of the ball after the 5th bounce. So it's helpful for a question like this to have a picture. So we'll draw ourselves a little picture here. It doesn't have to be anything fancy, really just something to give you an idea of what's happening. So here's our 4.0 meters, and I don't like how I did that. Here's our 4.0 meter height, right? And the ball, let's do this in a different color. The ball's just dropping off the top, hits the ground, bounces, and it says that it bounces back up to 60% of its previous height. So there's the first bounce, right? First bounce. Then it's going to go up, come down again, right? However much it went up, it'll come down the same distance. Hit the ground again a second time. Right, go back again, and then down for the third bounce, up, oops, that's too far, up 60%, and then down for the fourth, and then there is your height after the fifth. I think I got to do one more actually. Down, there's the fifth, and up. There we go. Let me put that one in a different color, because we are asked about the height after the fifth bounce. So as soon as it hits the ground for the fifth time, that red line is that height we care about. So 1, 2, 3, 4. 1, 2, 3, 4. It looks good. I've got all the bounces in there. So this is what is essentially happening. I know my picture's not great, but it gives you an idea of what would be happening, right? So there's the height we actually care about. So if you think about this in terms of a sequence, well, if I'm looking for the height of the ball after the fifth bounce, we can really talk about this if I just look at the height of after each bounce only. So the height after the first bounce, height after the second, height after the third, height after the fourth, then height after the fifth. That is the sequence that we're going to care about. The 4 meters isn't going to be part of it because that's the initial height I'm starting at. The ball hasn't bounced just yet. I don't know what 60% of that height happens to be. That's going to be the first term in the sequence, right? So this is going to be 60% of 4.0. My second one is going to be 60% of 60% of 4.0. Right? That is my first term, 60% of 4.0 right here. But I need to have 60% of that because I only rise to 60% of my previous height. And we're going to keep doing that pattern all the way down. Of is the word in multiply, or word in math that means to multiply, right? Groups of is how you learn how to multiply in the first place. So I can find out what this first value is, that term 1, by doing, 60% of 4.0, which really means 0.6 multiplied by 4. So the first term here is 24. Right? I guess really it's 24 meters. Right? That's going to be the first term. That is how high this ball reaches after the first bounce. Now the ratio here, it's always in terms of 60% of your previous height. So 60% of 24 will get me height number 2. So my ratio here is going to be, 60%, which is the same thing as 0.6. Right? There is my ratio. That's what we're multiplying by. So now that I know that, Tn is equal to T1 Rn minus 1. So my general term is my first term of 24, ratio of 0.6, and minus 1. There is the formula that will allow us to find out the height we actually need. How high is it after the fifth? Okay, so we're really looking for the fifth term here, right? Which means that if we translate all that information, that means the fifth term is equal to 24, 0.6, 5 minus 1, right? N is going to be 5 because I'm looking for the fifth term. And let's put this in a calculator to make sure we've got all the pieces where they need to be. So 24 brackets, 0.6, close them. 5 minus 1 is 4, so there's my power 4. There is your number. Doesn't say to round to anything. The number's not too large, so we'll write it all down. So that fifth term is 3.1104 meters. Okay, so there is how much it will rise after that fifth bounce. That is the height that it will reach. So the ball reaches a height of 3.1104 meters after the fifth bounce. And there you go. There is some things that we can do with our geometric sequences. A little bit of the differences between geometric, arithmetic. There's applications to both of them. This one ends up being a little bit more interesting in terms of multiplication and that application it has to real life contexts. So again, you'll find the links in the description box. In our next one, we'll talk about geometric series and what that might mean of adding up all those terms in a geometric sequence, what that formula looks like. So enjoy the rest of your day, and we'll see you back here in the next one. Bye-bye.